You cannot look inside an atom without changing it. This is not a limitation of your instruments. It is not a problem waiting for better technology to solve. The act of observation itself, at this scale, fundamentally alters what you are trying to observe. The universe, it seems, does not permit passive observation at the quantum level. This is not philosophy. This is measurement. Most of us imagine an atom as a tiny solar system, a dense nucleus at the center, electrons orbiting in neat paths around it like planets around a sun. It is a comforting picture. It suggests that if we could only build a microscope powerful enough, we could watch these electrons trace their orbits, measure their positions, clock their speeds. We imagine we could observe them the way we observe the moon. But that picture, as appealing as it is wrong. Not slightly wrong, fundamentally wrong. An electron does not orbit an atom the way a planet orbits a star. Before you measure it, an electron does not have a definite position. It does not have a trajectory. It exists, in a very real sense, as a cloud of probability spread throughout space. It is nowhere in particular and everywhere at once. When you try to locate an electron, when you shine light on it or pass it through a field to measure where it is, something remarkable happens. The electron suddenly has a position. The cloud collapses. The wave becomes a particle. But here is the cost. The moment you know where it is, you lose information about where it is going. The more precisely you pin down its location, the less you can know about its momentum. This is not a trick of measurement. This is the way reality behaves at small scales. This principle has a name. We call it the uncertainty principle, but that name is misleading. It suggests our knowledge is uncertain. That is not quite right. The uncertainty is in nature itself. The electron does not have both a precise position and a precise momentum to be known. Those properties do not exist simultaneously with arbitrary precision. The universe does not store that information. When you measure one, you disturb the other. Not because you are clumsy, but because measurement is interaction and interaction is change. Think about what it means to see something, to see this page. Light bounced off it and entered your eye. The page is large and heavy compared to a photon. The act of seeing it does not noticeably move it. But an electron is not a page. An electron is so small, so light, that a single photon carries enough energy to knock it somewhere else entirely. To observe is to touch. To touch is to push. At the atomic scale, there is no such thing as a gentle glance. You might think we could use gentler light, dimmer photons, lower energy. And you would be partially correct. Lower energy photons disturb the electron less. But lower energy means longer wavelength. And longer wavelength means the photon is physically larger, more spread out, less able to pinpoint exactly where the electron is. You gain precision in momentum, you lose precision in position. You cannot win. The universe has structured itself such that perfect knowledge is impossible. Here is where it becomes strange in a way that defies comfortable explanation. Before you measure an electron's position, it genuinely does not have one. It is not that the position is hidden from you. It is not that the electron is really somewhere and you just do not know where. The electron exists in what we call a superposition, a state where it occupies many positions at once, weighted by probability. Only when you measure does it choose a location. This is not a metaphor. Experiments confirm this again and again. Send a single electron toward two slits in a barrier. Do not measure which slit it goes through. The electron behaves as if it goes through both slits simultaneously, interfering with itself, creating a pattern on the detector screen that only makes sense if the electron was in two places at once. Now measure which slit it passes through. The interference pattern vanishes. The electron goes through one slit or the other, like a particle, not like a wave. Observation changes the outcome. You may feel a rising discomfort. How can observation change reality? What counts as observation? Does the universe require a conscious observer? The answer is both simpler and stranger than that. Observation in physics means any interaction that extracts information. It does not require consciousness. A photon hitting an electron is an observation. A detector clicking is an observation. The universe is constantly observing itself, particles interacting with particles, collapsing possibilities into actualities, without any need for a mind to witness it. But this raises a deeper question. If the electron does not have a position until measured, what is it between measurements? We describe it with a wave function, a mathematical object that encodes probabilities. The wave function spreads through space, evolves over time, passes through multiple locations. It is real in the sense that it predicts experimental outcomes with extraordinary precision. But it is not a physical wave in the way a water wave is. It is a probability wave. And when you measure, the wave collapses to a single outcome. Why does it collapse? No one knows. This is called the measurement problem, and it remains one of the deepest puzzles in physics. We can describe what happens. We can predict the probabilities with perfect accuracy, but we cannot explain why measurement causes collapse or what collapse really means. Some say the universe splits into many branches, one for each outcome. Others say the wave function was never real to begin with, just a tool for calculation. We do not know. The math works. The mechanism is a mystery. What we do know is this. The smaller you go, the stranger things become. At human scales, objects have positions and speeds, and you can measure both. A baseball does not cease to have a location when you are not looking at it. But a baseball is made of atoms, and atoms are made of particles, and those particles obey quantum rules. The reason you do not see quantum effects in everyday life is not that they are not happening. It is that they average out. Billions of particles, each with its own quantum uncertainty, combine to produce something that looks definite and classical. But at the atomic scale, you cannot average out. You are dealing with individual particles, single events, discrete clicks of a detector. And at that scale, the rules are different. Position is fuzzy. Momentum is probabilistic. Cause and effect blur. A particle can tunnel through a barrier it does not have enough energy to cross, simply because its wave function extends to the other side. And sometimes the improbable becomes actual. You cannot think about atoms the way you think about objects. An object is here or there. An electron is smeared across space until a measurement forces it to commit. An object moves along a path. An electron takes every path simultaneously, weighted by probability, until you observe it and the paths collapse into one. An object exists independent of observation. An electron, in a very real sense, does not. This is not a failure of human imagination. This is nature showing us that our intuitions, built from experience with large, slow things, do not apply everywhere. The universe at small scales operates by different principles. And those principles are not merely mathematical abstractions. They have consequences. The stability of atoms depends on the uncertainty principle. Without it, electrons would spiral into the nucleus and matter would collapse. Chemistry, biology, you exist because the universe forbids perfect knowledge. You may wonder if this means reality is subjective, that observation creates the world. It does not mean that. The wave function evolves according to precise laws, whether or not anyone is watching. Particles interact, systems entangle, outcomes occur. What observation does is select from all possible outcomes one actual outcome. But the rules governing which outcomes are possible and how probable each is, exist independent of observers. The universe was computing probabilities long before there were minds to wonder about them. Still, there is something unsettling about the idea that nature itself is probabilistic, that at its core, the universe deals in likelihoods, not certainties. That God, as some have said, plays dice. You may prefer a universe where everything is determined, where the future is fixed by the past, where perfect knowledge is merely difficult, not impossible. But that is not the universe we inhabit. Experiments have shown this beyond reasonable doubt, and perhaps there is something liberating in that. The future is not written in the stars or in the positions of particles. It is genuinely open, not just unknown, but unknowable, because the information does not exist yet. Quantum mechanics tells us that the universe is creative, that it generates new information with every measurement, every interaction, every moment. Reality is not a film playing out a predetermined script. It is an improvisation. But we should not overstate this. Quantum randomness does not give you free will. It does not make the universe magical. It is randomness, not purpose, probabilities, not intentions. The electron does not choose where to appear. It simply appears according to the rules, and the rules are mathematical. The universe is strange, but it is not arbitrary. It follows laws, even if those laws permit outcomes we cannot predict. When you look inside an atom, you find that the observer and the observed are not separate. They are entangled. The act of measurement is a physical process, and it leaves both the instrument and the particle changed. You cannot stand outside the system and watch. You are part of the system. Your measurement device is part of the system. There is no view from nowhere, no perspective outside the universe looking in. We are inside, interacting, changing, and being changed. And this, perhaps, is the deepest lesson. The universe does not reveal itself to passive observers. It responds to interaction. Knowledge is not a picture taken from a distance. It is a conversation, a give and take, a disturbance and a response. We learn about nature by touching it, and in touching it, we alter it. This is not a bug. This is how the universe is made. The idea that observation changes reality sounds mystical. It is not. It is mechanical. Photons carry momentum. Interactions transfer energy. Fields disturb fields. At small scales, these disturbances matter. They are not negligible. They are the signal. What we call observation is simply the universe interacting with itself, exchanging information, updating probabilities, collapsing possibilities. You may never feel comfortable with this. Generations of physicists have struggled with it. It violates our deepest intuitions about reality, about objects, about knowledge. We want things to have properties, whether or not we measure them. We want the moon to be there when we are not looking. And the moon is there, but the moon is not an electron. The moon is vast, averaging over quantum uncertainties so thoroughly that it appears classical. The electron is not. The electron shows us the rules beneath. So when you look inside an atom, something very strange happens. Not because atoms are magical, but because they are small. Not because observation is supernatural, but because it is physical. Not because reality is subjective, but because interaction is fundamental. The universe at the smallest scales is not the universe of common sense. It is a universe of probabilities and wave functions, of superpositions and collapses, of limits on knowledge built into the fabric of space and time. And we live in that universe. Every atom in your body obeys these rules. Every photon striking your eye, every electron firing in your brain. The strange is not distant. It is here, now, beneath the surface of the familiar, holding you together, making chemistry possible, making you possible. You are, in the deepest sense, a quantum phenomenon. When you look inside an atom, you are looking at the foundation of your own existence. And it is far stranger and far more wonderful than anyone imagined.